Reinforcement learning from human feedback has become the backbone of modern LLM alignment. But there's a quiet vulnerability in the pipeline that's been consistently overlooked. Reward models are typically trained as deterministic point estimators. They spit out a single scalar score for every prompt-response pair, and they have no internal mechanism to signal when they're making a confident judgment versus when they're essentially guessing. Meanwhile, modern policy optimization methods like group relative policy optimization, or GRPO, standardize these rewards uniformly within each rollout group. The result is a structural mismatch. When the reward model is uncertain, GRPO treats that uncertainty as equally reliable as a confident prediction. And when a confusing, out-of-distribution response gets a spuriously high score, the uniform standardization amplifies it, pushing the policy to exploit that unreliable signal. That's reward hacking, and it's a primary driver of unstable training and misalignment. So the core question is straightforward. How do we make the policy aware of when the reward model is unsure? Prior work has explored ensemble methods or standard conformal prediction, but ensembles are computationally prohibitive for online RLHF loops, and classical conformal methods struggle with the conditional, sample-specific reliability signals that advantage computation actually requires. We need a framework that quantifies uncertainty efficiently, calibrates it with distribution-free guarantees, and directly integrates it into the policy update. That's exactly what uncertainty-aware reward modeling, or UARM, does. Here's how UARM actually works, starting with the reward model itself. Instead of predicting a single scalar, UARM parameterizes the reward model as a quantile regression estimator. It outputs a set of conditional quantiles for the reward distribution given a prompt-response pair. These quantiles are trained jointly by minimizing the pinball loss, which asymmetrically penalizes under- and overestimation depending on the target quantile level. The median quantile serves as the point reward, but the real signal is in the spacing between consecutive quantiles. Narrow intervals mean the model is confident. Wide intervals mean the reward distribution is skewed, sparse, or fundamentally confusing to the model. But raw quantile spacing isn't enough. We need calibrated, distribution-free coverage guarantees. So UARM uses a conformal prediction procedure on a held-out calibration set. For each calibration sample, we compute a conformity score, the minimum number of consecutive interquantile intervals needed to cover the observed reward. We then set a threshold based on the empirical quantile of these scores. This gives us a prediction interval for any new rollout that satisfies conditional coverage guarantees. Crucially, the width of this interval adapts per sample. It expands automatically for responses that fall in low-density regions, giving us a precise, instance-wise measure of predictive uncertainty that standard point estimators completely miss. Now, how do we actually use this uncertainty during training? This is where the second phase of UARM comes in, and it directly addresses GRPO's biggest flaw. In standard GRPO, advantages are computed by subtracting the group mean and dividing by the group's standard deviation. This assumes every reward signal has the same reliability. UARM replaces that uniform standardization with a heteroscedastic advantage reweighting scheme. Here's the math behind the fix. We treat the conformal interval width as a direct proxy for observation noise. Under a local Gaussianity assumption, we convert that width into a per-sample observation noise variance. The naive group variance conflates true signal variation with this measurement error. So we decompose the observed variance into a signal component and a noise component. We subtract the average observation noise from the total variance to isolate the genuine reward differences, adding a small stability constant to prevent numerical instability during optimization. With signal and noise separated, we construct the uncertainty-aware advantage. We multiply the standard GRPO advantage by a reliability weight, the signal variance divided by the sum of signal variance and the sample's specific noise variance. This ratio is the key. For high uncertainty samples, the noise variance is large, so the weight approaches 0, effectively suppressing their influence. For confident samples, the weight approaches 1, preserving the full advantage magnitude. This plugs directly into the GRPO objective, with negligible computational overhead. No ensemble forward passes, no density estimation. Just a clean, mathematically grounded downweighting of unreliable signals that prevents the policy from chasing spurious outliers. We tested this across 3 major preference datasets: HelpSteer, UltraFeedback, and PKU-safe RLHF. The results are consistent and statistically meaningful. When we rank predictions by estimated uncertainty and evaluate only the most confident 50%, UARM consistently outperforms both model-based methods like deep ensembles and distribution-free methods like standard conformalized quantile regression. We see significant gains in R-squared and substantial reductions in mean squared error and mean absolute error. More importantly, in practice, this translates to stable training. The reward model stops overfitting to confusing formats or verbose hallucinations. The policy stops exploiting unreliable signals, and the alignment process actually converges to more helpful and honest behaviors. Reward hacking isn't just a bug in RLHF. It's a structural consequence of treating uncertain predictions as certain facts. UARM shows that by moving from deterministic point estimates to calibrated quantile intervals, and by explicitly separating signal from observation noise during advantage computation, we can stabilize the entire pipeline. This isn't just a marginal improvement. It's a necessary step toward reliable, scalable alignment. If you're working on RLHF, GRPO, or reward modeling, this framework is worth implementing. The full paper breaks down the theoretical guarantees, ablation studies, and implementation details in depth. Check the link in the description, and let me know in the comments how you're handling uncertainty in your own alignment pipelines. Thanks for watching.